Hello and welcome to episode 2 of the Oxford Online Maths Club. My name is Dr. James Munro and excitingly today I'm joined by a guest. Let me get them on screen now. There we go. I'm joined by David. David, say hello.
Hi.
Hi, I hope people can hear David as well as me. I've tried to plug everything together. We'll see if that works. David's a first year student at Oxford. That's right, isn't it, David?
At St. Peter's.
At St. Peter's College.
Duddle.
Oh, wearing the St. Peter's crest and everything. Fantastic stuff. So David's kindly volunteered to be on screen doing some maths with us. Cool, right,
Yeah.
okay. Are you excited? How do you think it's going to go?
I mean, I feel like I'm back at interviews, but I mean, it should be chill, right? It should be. It shouldn't be that bad.
Yeah, we're going to try and keep it a bit chill. We're gonna do some maths, but nobody's being interviewed, and it's not going to count towards your degree, right?
I mean, I would hope so.
In David's defence, it's the start of Oxford's term. It's the first week of Oxford's term. David's had a nice long break over the Christmas holidays and the New Year. We're getting back into speed. Right, okay. Let's have a look at what we've got coming up today. So coming up, my helpful volunteer is going to be trying some unseen math questions. These are math questions that David's never seen before, and I'm hoping they're math questions that you've never seen before. More about where I got them from in a moment when we get to it. Coming up after that, we've got Return of the Squares, where I'm going to go back and look at the squares problem from episode 0. After that, we're going to look at Return of the Cubes, going back to a problem with cube numbers that, a problem with cubes from episode 1, which I don't think David's seen before. So it'll be a surprise for everyone. Right, okay, but first up, we've got a question that David has never seen before, which I'm going to try and get on screen now. There we go. Wish me luck. Okay.
Wish
Here's
me
our
luck.
whiteboard. Are you in the whiteboard as well?
Yeah, okay. Yeah, I've got.
Can we see your cursor on screen? Is this set up? I mean, this whiteboard has intentionally been left blank, and we're supposed to turn it over. Cool. Right. Good.
But this is so. Yeah.
Almost like there you are. Hello. Cool.
There.
Great. Look at that. What wonders technology can do. Right. Okay. Are you ready? There's going to be a math question appearing on screen. So quick note before I give the math question to David about where I got this from. This year we set an extra little math-like question paper for a few candidates at interview. So some people missed the math, but we shortlisted them anyway, and we gave some people the chance to do an extra bit of math. That meant writing some extra questions. So we wrote some extra math questions, just like we write normal math questions. I'm going to show you some of these today. If you're in year 11 or year 12 and you're watching at home and you've never heard of maths before, it's our admissions test that we use for maths. The questions are hard. The question we're about to see is tough. I'm giving David a way out. The question we're about to see is tough and might not happen straight away. I have also forgotten to say that you can join us live in chat below at slido.com/OOMC if you want to get involved with whatever's going on underneath. Oh look, here's Alan Turing, who's asking me what I did my PhD in, but not right now, wow. Alan. I'm busy. Right, okay. Here's a math question. So I'll read it out. I'm not sure how the screen quality is. Using degrees, says the question. Math questions are all written using degrees, but this one is extra careful about explaining that it's using degrees. The number of real solutions x to the equation, and then here's a horrible equation, cosine of 240x divided by x squared plus 4 equals exactly 1/2 is, so the number of solutions is it 0, 1, 2, 3, or infinitely many? Cool, okay. Oh, anonymous person who's missed out on previous episodes, you haven't missed anything too important. They are still on YouTube. And when we talk about the problems, I'm going to explain what the problems were again. So you haven't missed anything too important, but you can go back and watch. Nice to have you with us, anonymous person who's joining in on episode 2. I'm talking to give David time to think about how to get started with this problem. David, what do you think about this problem?
This reminds me of a horror movie that I was watching.
Oh yes, okay. Very math-specific horror movie.
Right. I mean, I see that 240. That's a bit suspicious.
Okay.
Because it's just such a nice multiple of 60. So
Cool.
Um,
Three facts. Okay. And 60
yeah,
degrees is a thing we know facts
yeah,
out, right? Yeah. Okay. I think
yeah.
that's a good point.
So, but I mean, I don't think that really matters. I think we just have to see. Well, you know, we could just like draw a graph of cos and what cos is.
Yeah, that seems like a good. That
Uh,
seems like a good idea. Should we try and fit that in this bit underneath the options?
yeah. So wait, can you see? Yeah. Oh wait, no, I should make. I should. How do I erase this? Oh, here I am. Okay, cool. So, like a graph, right? Let's see what cos looks like. And cos goes something like that.
Yeah, classic.
Um,
Bucket shape,
now,
nice.
bear in mind this is in degrees, so it's going to be a bit tricky. Okay, so, well, if we were in radians, then this would be, well, this would be pi, and this would be 2 pi, right?
Yep.
This would be pi.
Worth saying here, I suppose you're allowed to use radians as part of your solution. This question is in degrees. So how many degrees is pi radians for people who don't know about radians?
Oh, pi radians is 180 degrees, I think.
Ah, right. Okay, cool.
Right, so this is the conversion. So pi radians, it's called like radians, or like I don't know how it's called. Yeah, and that's just like basically 180 degrees.
Cool.
Degrees. Anyways, so if we were in radians, then we could. Well, if I want cos to be a half, then I want to have these two solutions.
Okay.
And
Okay.
we know exactly those solutions, which is in degrees it would be 60 degrees and 300 degrees,
Okay. Cool. Okay.
right?
So looks like we got 60 degrees, 300 degrees. I guess there's more solutions if we keep drawing cosine wobbles over here, and we get sort of
Yeah, yeah, of course.
yeah,
Yeah,
got some more. Cool. Okay. I've remembered.
right.
just while you think about more values of cos, just to
Okay.
explain what's gone on here below, I've turned on a poll in Slido for people to vote for what they think the answer is. I didn't realise that would replace chat on screen.
Oh, wow.
So chat will come back on screen in a minute, and we can still see your questions. Christian and Flora are in chat as well, answering questions. Sorry, you were telling me about 60 degrees. What do you want to tell me?
Yep. Um, well, I mean, I think now we should have a look at what's inside cos. And so inside cos is 240x over x squared plus 4,
Uh-huh.
right? And how that goes, maybe.
Yeah, where is that? Yeah, we could try and draw a graph of that, I suppose, if we wanted to, or we could think.
Yes, I think so. So I'll
Do you want to go down a bit? I can pan.
yeah, of course. I'm
Right,
already right.
there you go. There
Yep.
you go.
Okay.
So drawing.
So let's see how that would look like.
Is this going to
Let me
be
just zoom in.
x squared plus 4, perhaps?
Yep. So, well, the denominator goes towards infinity quicker than the top of the fraction. So eventually it will go to 0.
When x is really big, then this gets really,
Yeah.
really small
Yeah.
because
Yeah.
x squared gets big faster than x.
It should have a maximum because it's continuous.
Sure. So it's 0 when x is 0. It's
Yeah.
very small when x is very large. Somewhere in between.
Infinity, and then somewhere in between does something, right?
Okay. Okay.
Um,
I actually think
but
that's
the
enough to get an
question is-
idea of the shape of it.
Yeah. So the question is, what is the maximum of it? And then we can compare the range to the well, what cosine has as an input.
Yeah, so that's an idea. So we could look at can this thing be well, so with the 240 in there, can this thing be equal to 60 degrees? Can it be equal
Yeah.
to 300 degrees? Can it be equal to whatever the next one is?
Yeah.
I'm going to encourage you then, because you're first year and you know loads of calculus, you probably know how to differentiate this and find its maximum.
So
Some of the people watching don't know about differentiation.
Okay.
So extra challenge, we're going to try and do this without finding the maximum of it. I think we don't need to know technically exactly where the maximum is, so it's going to be okay.
Okay.
I'm just thinking of the year 11s watching who maybe don't know about differentiation. Extra challenge, sorry.
Right.
Okay. Should we try and sketch this?
Okay. So it should be something like that. Whoa. Okay.
Where are you?
Should be something like that, I guess.
Yeah, something like that, isn't it? Yeah.
Yep.
So when x is 0, this is 0.
Yep.
When x is really big, it gets really small. But there's some maximum value it takes.
Yeah.
Like that, somewhere in between. And if we knew some calculus, we could find out what it is. I guess this means thinking about the structure of where we're going with this. That we were thinking a little bit about whether it could hit 60 degrees, whether this thing inside the brackets could hit 300 degrees. But we're not going to need to check infinitely many of these numbers. You know, there's infinitely many solutions. Yep. Cos thing equals 1/2. But this thing inside has got some maximum. So some point where, are we going to consider 3000 degrees? Probably not, because this function probably doesn't get that big. Okay.
Yeah. Okay, so, well, we know that because we have a 240 factor in there, like we could say, for example, like, you know, take x equals 1.
Yeah, okay. Okay, right,
and
wow.
Then, right. So take x equals 1. And when x equals to 1, we have 1 over 5 times 240. So we have, I always do this. Okay, so we have 240 over 5.
I think that's 48, isn't it? Which is
48, which is less than 60.
Yeah, it's a little bit small. I suppose is this ever equal to 60? Because if this never makes it up to 60, or with the 240 in there.
Yeah.
Let's put the 240 in. If this never makes it up to 60, then I guess we're done, because if it never makes it up to 60, there's no solutions.
Yep.
Okay. What do you think?
So we could just use the discriminant to see whether it's actually reaching 60 or not.
Right? Yeah. Okay. Yeah. Seems good. Seems like quadratic equations, right? Somebody in chat just said. Somebody in chat, not on screen, but somebody in chat just said they're in year 10. I think even year 10s know about quadratics and discriminants.
Yeah, they should. Right, so we have 240 x equals to how many? 60.
Yes.
So 60 x squared plus 240.
Is there a?
That's 4 times.
Yes, 4 times 60. Yeah, cool.
Yeah. And then we can divide through by 60.
So we're at the point of this question now where we've had the idea of checking the discriminant of a quadratic.
Yeah.
But we haven't. We've still got to actually get it right. X squared plus 4, you divide through by 60.
Yep. So we have x squared minus 4x plus 4 equals to 0.
Cool. Okay.
And this is just x minus 2 squared. So x is 2.
Brilliant. Yeah, it's a repeated root actually.
Yeah.
Cool. Okay, so we've got x equals 2. In fact, because it's a repeated root, I think that means that we've actually secretly found the
it's the maximum.
Yeah.
It's the maximum, yes.
Yeah. Is with the 240 in there, that's exactly 60.
Yep.
Great, so this function doesn't get as big as 300. We don't need to worry about other bigger values of cosine, right? Okay, so we've got x equals 2.
So then we know, like we have, so we don't, I'll just go back to the, to here. Yeah. So this is how we're going to go. I'm just going to draw it with a red pen, because why not? So we're going to start off at 0, and then we're going to go here, right? And then we're going to go all the way up to 2, right?
Yep.
And then we're going to reach this point, and then we're going to go backwards.
Yeah, so as you change x, the thing 240x over x squared plus 4, as you
and
change
you
x from
backwards.
0 up to infinity, you go up and then come back down again. Okay.
So there's only
So
one value.
there's one value. Okay, let's be really careful
No?
because we're looking for all the real solutions, and we've thought about what happens when x is positive, but I'm a little bit worried about what's going on when x is negative. I'm just not sure we've thought
Oh,
about
well,
x being
yeah.
negative yet.
Yeah, that's true. So two values then.
Two values, yeah. I think we pick up.
Yeah.
I think we pick
So
up by
we
some sort
could
of symmetry, right?
use symmetry, yeah. There's the other one. So that's at -2.
Yeah. Okay. So we've got a solution when x is
Yeah.
minus two, when x is minus two, and a solution when x
Yeah.
is two. This thing inside the brackets here, we did a good sketch of it for x positive. We should maybe also have thought about x being negative and how this gets down to -2, which is interesting because cos of minus 60 degrees is also 1/2. Okay, I think this means we pick up two solutions in total. I guess our final answer is C. Let's see if the audience agrees with us. I've had the voting secret so far. I'm not going to reveal the number of votes for each option. Let's see what they think. Woof. Is that on screen? Oh, okay. So C is the most popular answer with 102 votes.
Yeah.
Total 44 people have picked C. Two solutions. Maybe thinking of x is 2 and -2 as well. Lots of people. Next most popular option there is B. Just one solution, which is where we almost landed on thinking about 2.
Yeah.
And I guess the trick there was to think about negative solutions as well. I suppose you could pick C2. It's almost funny that you could pick C2 if your quadratic had gone a bit wrong. Because these are multiple choice questions, if you make multiple errors, you can sort of end up at the right answer.
Yeah, exactly.
I wonder if there's
if
anyone...
you have like a wrong factorization and then you have two roots.
I wonder if there's anyone in chat who maybe got the wrong quadratic and got two roots, but wasn't also thinking about negative 60 degrees. I don't know. Okay, so this is a look at a math question with negative numbers. Somebody in chat says, well done, and chat, which wasn't on screen, but was, I think, quite concerned about us. Okay.
This was fun.
Yeah, it was good enough. I tried to pick. Oh no, go. Sorry.
Yeah. I said it was really nice to see how so as you go like the input is from a function, and as that varies, you literally just go forwards first, and then you go backwards.
So it's like
I don't know. It's really nice.
I've seen similar things asking about things like sine of x gets you to think about that in a similar way. It's sort of a function of a function. So you need to think about how the inside thing changes and how the outside thing changes as well. Okay. Reasons I included this question, sorry, just to defend it a bit. I like that it's got a function inside a function. Oh, sorry, we've changed slides. Give me a moment. We've got a function inside a function, and that feels quite unfamiliar. This is not something that I would expect people to be able to just sketch off the just by looking at it. It's supposed to be a bit unfamiliar and surprising. But actually, when you start playing with it to find these solutions, it becomes simpler. And that's a pattern that I've seen in a lot of math questions. That you start with and it very quickly gets very difficult as you read the question. It's sort of really hard to get started, but then you start having ideas, and if you can get over that initial, I don't know what to do, and sort of first we sketched cos because we wanted to think about cos, then we sketched this function down here because we want to think about the thing inside, and by piecing things together, we got there in the end. So in a way,
the question itself looks bad.
The question looks bad. Yeah, you just had a sneak peek at the next one, so I've also picked a second one that looks bad.
Literally didn't read it.
People in chat, let's see if I can catch up with people in chat. Ro says, Ayo, I got a question right. I am ready to go to Oxford right now. Sign me up. Grand, yeah. Feel free to apply in the next cycle in October, he says, as admissions coordinator. Yeah, somebody here, Anonymous, says, how did you decide that x equals 2 is a maximum? I didn't really say anything about it, but let's go back and have a look. So, David was doing the algebra, and David got this repeated root. Okay. Do you want to explain it? Go.
Yeah, so see how we got... So everything at the end boiled down to this quadratic. X minus 2 equals 0. Right? And that means that... So you sort of have... well, this quadratic, right? So you have x minus 2, like that.
Yep.
And that's where that happens, right? So that means that you have a repeated root. So because there's a relationship between this graph, this x minus 2 squared equals 0, and this graph, that means that this has to be the maximum. It's a repeated root, and therefore it is a maximum.
Yeah, okay. Yeah, I
Right?
suppose
No?
yeah, absolutely. Said differently, I suppose is the key thing is we were solving for equals 60 degrees. If we were solving for sort of equals 50 degrees or something, we'd get a different quadratic out, and I guess it would have two solutions. So I was sort of expecting two solutions, because normally when you draw a horizontal line y equals c across here, and you set constant equal to, I guess, x over x squared plus 4 or something. Normally I was kind of expecting two solutions out. When I saw David had got one solution out, that gave it away to me that we were in a very special case. We'd taken y equals c and just got one solution. It's pretty unusual.
Equally, like we could have gotten 0 as well.
Yeah, we could have got
if the line was above, then...
Which lines up with this thing Karen has just asked in chat. Why don't we consider 420 degrees or things with higher degrees? Because 420 degrees is way up here.
Way above.
So we could see from our sketch that you're not going to get any more solutions up here, that the function just doesn't get big enough. Its maximum was here. You could actually, I suppose, go back and check trying to solve this equation. This quadratic has got no roots, it turns out. So we kind of skipped over a little bit of steps. Three upvotes here for somebody saying, am I being thick, or is it possible to also do it by multiplying both sides by inverse cos? Not thick at all, just got to be quite careful with inverse cos. So I suppose the trap is, if you say this is...
You get plus or minus 60 degrees, right?
Yeah, inverse cos, well, there are lots of different angles that have cosine.
They can't see your screen.
Oh, they can't see the screen. I've gone off.
Yeah, just a bit
Thank you.
Yep.
That is the producer in my ear voice that I've needed for a few weeks now. So I suppose taking inverse cos of each side, there are some issues that, well, maybe this angle inside could be 60 degrees, or it could be 300 degrees. It's why David was very careful drawing the graph to say, well, there's lots of different numbers that cos of that number give me 1/2. If you type inverse cos into your calculator or something, then it only gives you one number back. But that's like losing information. It's a bit like the difference between if you want to solve x squared equals 9, then you can't just do the square root of each side, because just doing the square root of each side might give you something like x equals 3. Because there's sort of multiple numbers that square to 9, and there's multiple numbers that cosine to 1/2. Cool. Very quickly, I saw some other things come up in chat. Somebody asked, but not for real, so don't get excited.
I know.
I saw somebody ask, is all of the math like this? We do 10 multiple choice questions at the start and then 5 longer questions. Okay. Good. How do we draw x over x squared plus 4? Bit of experience. We thought about small and large values, and then we kind of joined the dots with only a couple of dots. We thought about what was going on at 0, what was going on for very large x. This technique of thinking about, we got one dot and we've got one bit of curve over here for large x. So I've got to join that up by saying, well, it's positive and it starts at 0. It's got to go up, I suppose. And then eventually it's got to come down again because it's very small when x is large. Help if I could actually write properly. Right, okay. I made a mess of this slide. Brilliant. Yeah, so positive. Importantly, we've got to think about 60 degrees, 300 degrees, and also minus 60 degrees. Person on screen now. Why does it go down and then back up? Well, I suppose when David was talking about down and back up again, we were talking about how this function inside, 240x over x squared plus 4, it kind of goes up, increases and then decreases.
Up and then it goes back down.
So here with the red arrows, David's thinking about as x
so
changes.
You go left, you go right, and then back left.
This plot is now a little bit tricksy, because this plot is kind of theta on this side, where theta is equal to 240x over x squared plus 4, I guess. It's sometimes interesting to go back to these doodly sketches that you draw when you're thinking about the question, and then try and actually label them up and actually interpret what they were. You don't have to for a multiple choice question, obviously. Okay. Do you get marks for your working out on multiple choice? No, not for the mat. For the mat, it's all on whether you got the right answer or not for the multiple choice questions. We got these longer questions where you show you working. Okay. Oh, and catamorphism at the top here in chat knows how to differentiate. And knows how to differentiate x over x squared plus 4, which I was trying to avoid doing, but if you know how to differentiate, try this one at home. Right. Oh, look, homework.
Differentiate that.
Yeah. If you're feeling brave, differentiate the whole thing. Sometimes I set homework, and I need people to understand that it's not really like...
Include cos.
Oh, include the cos? Oh, include the cos. Okay. Sometimes I set homework, and I need people to understand that it's not really like homework I'm expecting you to do, and I'm not going to mark it. But hey, here's something to try at home if you want to. Right. More information on the map, by the way. If you, I bet Flora and Christian, I can't see them on my screen, but I bet Flora and Christian are in chat heavily answering questions about the mat, which is a 2.5-hour test, Alan Turing. Cool, should we do another one?
Yeah, why not?
Let's do another one. I've got one more loaded up. Okay, I'll read it out as well. give you time to read it. The following are statements about a real number x. So that's that real number x again. P colon. So this statement is named P. X squared minus 1 over x plus 2 is negative. And the statement Q is 1 plus x over 1 minus x is positive. Then it follows that. And now one of these 5 options is correct, and the others are not. So there's exactly one correct answer to this question. Is it true that P implies Q, but Q does not imply P? Is it true that Q implies P, but P does not imply Q? Is it true that P and Q are equivalent? So when one is true, the other is true, and vice versa. When the other is true, one is true. Is D true? Is D the right answer, which says if P is true, then Q is false. So there can only be one. Or if Q is true, then P is false, is option E. Right, okay. I'm not sure reading that out helped, because I think I made it more complicated by reading. Oh well, okay, right.
Okay.
Yeah, people in chat are not liking the homework. Chain rule, then quotient rule, ooh. Fun. Right, okay.
Yeah. Right. Well, I see. You know, we can check for what values of x is P true. So we can start with P, and then we can see whether that implies Q or not.
Okay. So yeah, I agree that P is this statement that might be true, it might be false. I think it's true for some numbers.
So let's check when it is true. I think.
Sure. Yeah, okay.
And then we can do the same for Q, but let's do it first for P. So we have x plus 1. I'm just going to write it this way.
Ha.
Right?
Mm-hmm.
And when that is less than 0.
Yeah.
Well, then we either need the top bit to be positive over something negative, or we need something negative over something positive.
I think I agree, yeah. Yeah,
right.
If we want this thing to be negative, then we need the to be true.
Yeah. So we have, well, x squared minus 1 looks like this. And it's negative, well, all over here in this region.
Mm-hmm.
So between negative 1 and 1. And, well, for x to be positive, I mean, for x plus 2 to be positive, well, x plus 2 is positive between negative 1 and 1. So
That's
between so for x in between negative 1 and 1, that's not that's a strict inequality. So we have this. So between 1 and minus 1, P is true. Right, so what about the other way around? We could have x plus 2 being negative, Wait, hold up. Okay. Yes, so we could have x plus 2 being negative, which means that x is less than 2, less than negative 2.
Okay, so you've got these two different cases.
Yeah.
And I suppose that identifies. Quite like this investigation at the start to identify when is P true. That we've been given some complicated statement about x. We could have tried sketching it, I suppose, or something like that. Sorry, I've been distracted by trying to also start a poll.
That's fine. That's fine.
Okay. Let's turn that one on.
So now we could check maybe Q as well. I mean, let's see if if x is less than 2. Well, if x is less than 2, then is Q true? So if x is less than 2, then Q is not true.
I've not got Q on screen. Sorry. Okay.
Sorry.
If x is
now,
if x is less than minus 2, why is Q? Tell me more about Q. Okay.
So Q. Let me just go down a bit. I'm gonna write it down. So we have Q. Oh, okay. So we have Q. Is x. Sorry. It's x plus 1 over x over 1 minus x, right?
Yeah, I think so.
Yes.
Let me just check.
Yep. It's fine.
Yep, good.
And we need that to be equal to 0. And the question is whether that is true or not. Well, if x is less than negative 2, then the top bit, so we have the fraction, and the top bit is negative.
Right, and the bottom bit is positive.
And the bottom bit is positive because negative makes a positive. So that is less than 0, which is like it's wrong. So Q is not Q doesn't hold.
Yeah, so I guess you proved that.
For 2.
P, I mean, yeah, I guess you've shown that if P is true. I'm trying to summarize everything on the screen at once. Sorry. If P is true, then Q might be true or it might not be true, which sounds like nothing, but it's not nothing. At
least we know that P doesn't imply Q.
Yeah, I agree. I agree so much. I'm going to write it on the screen. P does not imply Q.
And in fact, we also know that P is not equivalent to Q.
Yes. Okay. So it was looking good for our statements. I think that's not A and not C. Let me have a sneaky look at chat in the voting. Oh yeah. Okay. Yeah. Okay. So we think P does not imply Q.
Now, I say let's check between -1 and 1.
Yeah. Okay.
So let's see. So between -1 and 1, I'm going to have a number between -1 and 1, and I'm going to add it to 1.
Mm-hmm.
That means that it's going to be positive.
Yes, on the top. Yep.
And I'm going to have a number between -1 and 1, and I'm going to take it away from 1, which means that it's positive.
I need to think really hard. Sorry. Yeah, I agree.
Positive, right?
Yeah. Sorry.
And that's 0.
Great.
I mean, that's more than 0. So.
Okay. So sometimes
this doesn't tell us any more, but it's okay because at least now we know.
Yeah. Okay. Right? So you found some values there. Mm-hmm. If x is between -1 and 1, then we found that P and Q are both true at the same time, which is exciting.
Mm-hmm. But we know that, like from this we can, like, although we didn't get any information about whether P implies Q, we do know now that Q does imply P.
Oh, okay. Let's be
Let's
be careful because there might be. We've thought about x between -1 and 1, but there could be some other weird solutions to when Q is true. I think it's the right direction. Okay. Though. I think we should go and look at.
We can.
I think you're right, but I think we should be really careful about when Q is true.
Yeah. Okay. Yeah. I was just trying to you know, I was. It's often good to make a guess and then check the guess and then see whether that's right or wrong.
Yeah.
So I say let's check. Let's check
Mhm.
Q now because we've done P. Now let's do Q. Right.
Yeah, sure. Okay.
So again, we need a positive or a positive. So this is for Q now. So we need a positive or a positive, or a negative and a negative.
Yeah. Okay.
Right. There's only way we can get more than 0 as a fraction. So if we have positive and positive, that means that both 1 plus x and both 1 minus x are more than 0. And 1 plus x goes like, well, 1 plus x goes like that, and 1 minus x go like that. And when they're both more than 0 is between these two lines. So between -1 and 1.
I agree. Yeah. Which is exciting because it's the numbers that we had before.
Right?
Yep. So that's positive over positive. So that's
Yep.
sometimes when Q is true.
Yep.
What about negative over negative? Does that ever happen?
Negative and negative. Yep. So when we have, well, that doesn't happen, does it? Because there's no way. Well, we don't have both of them negative. Because when one grows very small, like very negative, the other one goes very positive. And it's just not going to happen. Like they're not going to be negative at the same time.
Right, yeah, okay. So this one never happens. So in fact, all of the solutions to when Q is true are x being between -1 and 1. Okay. Which is kind of what we wanted it to be.
So now we know. So now we know the answer.
Sure, yeah, I think so. Let's look back at the options.
Yep.
And then I can see people are voting in chat.
So I think it's Q. So now we know that Q implies P, but P does not necessarily imply Q.
Yeah, I think I agree. That's option B, isn't it?
Yes.
Option B. Cool. Let's check with chat. We've gone with B. Q implies P. That if Q is true, then x is between -1 and 1. So P is true, but P does not imply Q because x could be less than -2. That's our reasoning for B. Let's check with chat. What does chat think? Oh, chat's done great at this one. Look at chat. 80 votes. The votes are piling in now that the solutions are up. 80 votes and about 72 people have voted for Q implies P, but P does not imply Q. So I think we're in good company with chat. Nice job, chat. And somebody said something very clever in chat that I wanted to address. I'm going to turn this poll off so we can get chat back on screen. So somebody said we were done a while ago. I kept going. But somebody said, if D and E are false, this has got 3 thumbs up and everything. Let's see if I can scroll down and grab it. Oh, I can do this. Okay. Here's an anonymous person at the top. D and E are false, they say, because we've proven that they can both be true at once. Which is... I'm going to class that as a sort of hot take. Earlier on, when I think you said you were done, and I made you do a bit more. Maybe we were done, and I'm sorry.
It's fine.
Okay.
Right. I mean... it's always, no, because I mean, it's always better to check.
Yeah, okay.
Like, even if
this is false because we saw they could be true at the same time, and this is false because we saw they could be true at the same time, and I think that only leaves B. Am I right about A and C being? Yeah, we eliminated A and C, and if I've been paying attention, then D and E were also eliminated, so you're left with B. Right, cool. I made you do too much work. Sorry.
so when we finished B, like we knew the answer.
Yeah, okay. You did.
It's fine.
I can maybe imagine a thing where I hadn't paid much attention to the actual options that were worded. I can imagine a case where the options are more complicated and you don't get to eliminate 4 of them at once, and you actually have to think about whether P implies Q and whether Q implies P. Maybe not. Maybe if option. No, yeah, I don't know. Maybe we were done.
No. I mean, even if we were, if we were done, that's fine because now at least we know how to tackle problems that we like. If we have a guess, then might as well check it.
Yeah, okay. I think I've got some homework as well. it seems like I didn't. There was a point there where I didn't understand that we were done. So my homework, I guess, is that I need to go back and think about that point and think about how I could have spotted that we were done, that we'd ruled out all the cases. Great. Okay. I think I'll let David off Matt there. We're going to take a very quick break, and then we're going to look at some problems from episode 0 and episode 1. I hope you're hanging around. David, do you want to hang around?
Yeah, why not?
Sure, okay.
Yeah, cool.
I need to press the button. Wish me luck. The stream setup is extremely complicated.
Press the right button.
Okay. If I do that, does it appear on screen? No. Cool.
No, nothing
Great stuff. So in the break in the middle, I normally try and address some questions that have come up. People want an ad break. And there's a question there. How many people?
Ad break.
Yeah, I know. It's a terrible running joke. Okay, hang on. Let's do an ad break. Okay, totally not planned, but backed by popular request, it is the ad break, which is now on screen for you there. 10010 plus 101100. Great stuff. Right. Okay. Let's. So.
So confused. I thought they wanted the break.
They get an ad break. This is YouTube. It's all about rolling those mid-roll ad breaks.
That makes sense.
How many people sat this paper? So someone about 7 people sat this paper. I don't have an average score because only about 7 people took it. So we're trying to reuse the questions for other stuff. Cool. Okay. The two straight lines. Oh yeah. So Maya down here asks, what are the true straight lines? We're thinking about x plus 1 and 1 minus x, right? That was your graph of the top and the top and bottom of Q. Could you use process of elimination? Yeah, I think this is the idea that I wasn't paying much attention to what the options actually were, and if I'd been paying more attention to the options, we might have been done faster. Yeah, there's the anonymous person telling me to do this. Oh, somebody wants to try calculus. Fun. Somebody wants to put it into Desmos. Oh, multiply both sides of Q. The inequality is no longer the same. This is a true fact. Do you want to say something about what happens when you multiply both sides by 1 minus x? So the comment here is, if you multiply both sides of Q by 1 minus x, the inequality is no longer the same. Why is that?
Okay. But what, why would you multiply both sides? Like, if you multiply both sides by 1 over x, you don't know whether that's positive or negative.
That's true. There's also the problem that, you don't know.
Yeah.
Yeah. You don't know. There's a problem with, if you multiply both sides by a negative number, then that would flip the inequality around.
Yeah, so you don't know whether that's positive or negative, so you can't just multiply.
So in general, when you multiply both sides of an inequality, you've got to be careful to multiply by something you know to be positive, or be really careful. Cool. Anything else going on in chat? See, it's different to YouTube chat because I can scroll back through it. Dr. James, do you enjoy Oxford more than you enjoyed Cambridge as a student? It's that classic question about whether somebody's noticed that I studied at Cambridge. Always fun. Oh, people are telling me about binary and adding these numbers together. Oh, brilliant. Is this binary? And today's ad break is again brought to you by hexadecimal. Hexadecimal, 60% more digits. That's right. It's the same punchline as last week.
So is this decimal now? I mean, is this binary now, or what?
Well, no. So these are hexadecimal numbers. This represents 16. I didn't tell anyone, but this is hexadecimal. But this is a great feature of hexadecimal that it's got this kind of backwards compatibility. That some of the sums turn out to look the same as they would in binary, or even in decimal, or other base systems. That's one of the great features of hexadecimal.
What's hexadecimal again?
Hexadecimal is base 16. Instead of being worth 10, the next digit is worth 16, and this one is worth 256. They're sponsoring the live stream. That's why all of our ad breaks are in hexadecimal. Right, cool. Believe it or not, I think that's funny. Right, okay. Ad.
I heard that. Oh, sorry. Go on.
I'll do my ad as well. Promise Europe, not sponsoring the live stream like Space 16 is, but Promise Europe is a maths camp that Oxford is very involved in running. They've just put up some maths questions for people to have a go at. Even if you're not applying for Promise Europe, then there are some maths questions there for you to have a go at. If you like tricky maths questions, about number theory and primes and things. Are hexadecimal related to hex colours? Yes. Hexadecimal comes up in lots of variety of products and opportunities. Get your hexadecimal now. Right, okay. Do you think that people might believe that we're sponsored by Base 16? If I say it enough, people might believe that that's
they will.
Right, we've got about 15 minutes.
I think they already do. Yeah.
Okay,
I
great.
heard that actually there are three kinds of people: people who understand binary and people who don't.
Oh no. Like a twist on a terrible joke that's somehow even better. It's like round again.
Yeah, no, yeah.
Modular arithmetic. You've come back round to being brilliant again. Right, I'd like to address a couple of questions. A couple of weeks ago, I set this challenge question. I'm going to rephrase it slightly, but here's the question from episode 0. Are there two... Is this on screen? This is on screen. Are there two 6-digit square numbers with the same second digit, the same fourth digit, and the same sixth digit? Okay. So if you've got a square number, then this is like if I tell you the second digit, the fourth digit, and the sixth digit of a square number, can you always tell me what the square number was? And I got an email from someone called Joshua. Hi Joshua, if you're watching. Joshua wrote in with a brilliant email to say that they'd looked at some square numbers. I hope they had some code to look at this, but Joshua managed to answer this question in the negative. In the positive. Yes, there are. Yes, there are two square numbers with the same second digit, fourth digit, and sixth digit. So if you tried this at home, the answer is yes, there are two square numbers with the same second digit, fourth digit, and sixth digit. I suppose the answer to the original question is no, you can't always tell what this square number is, because there are these two. Other examples exist, but the ones that Joshua sent me are... Is Joshua in chat? Oh, am I glitching out? Ooh, are we breaking the stream? Someone in chat says I'm glitching, but like 20 seconds ago. Okay, this one is 320356. And this one is 125316. Am I gone?
Ooh. I don't know what's happening. It's glitching for me as well.
Okay. Is the sound still working?
Yeah, it is.
Cool. I'm going to try switching technology. Just the image. Okay, it's probably PowerPoint. Let's all blame PowerPoint. Joshua is here. Hi Joshua. There's Joshua, look. Cool, got some squares. With the same second digit, fourth digit, and sixth digit. Brilliant effort. So there's kind of multiple ways to do this question. A different way that I was imagining was
spreadsheet.
Yeah, okay. A slightly different approach, rather than looking for square numbers, that I'd like to show you quickly, because you can extend it to a similar problem with 8-digit squares. Okay, so I'm going to try and show you an alternative way to do this. It's going to look completely different. Okay, part 1 in my alternative way of doing this. So part 1 is to think how many 6-digit squares are there? And the answer to that is, well, to get a 6-digit square, you need to square something between, I think 312 less than or equal to n less than or equal to 1,000. In fact, not 1,000, because 1,000 squared is a million, and that's 7 digits.
7, yeah.
But I think 312 is just big enough to square to a 6-digit number. This is related to the square root of 10. This is the square root of 10 times 100. What I did was I thought about 10 to the 5, which is the first number that's got 6 digits, and I thought about its square root. Its square root is about 311, I think. So if you're 312, then you square to something with enough digits. Okay.
312 squared is 5-digit.
Oh, is it? Oh, how big's the square root of 10? Do I mean 313?
Maybe.
Let's up everything by 1.
Okay.
I appear to have forgotten the square root of 10. really cracking up for me, and
That's a 5-digit as well.
317. Oh, yeah, okay. People in chat, I'm going to try and swap technology and see if that makes things better. We're going to ditch PowerPoint. Wish me luck. We're going to switch back to this one.
17. Yep.
What's the square root of 10? Is it about 317?
370. So it's 317. It's not 312.
Ah, sorry, okay.
Yeah, okay, that's fine.
So these are the numbers that square to have 6 digits. Okay, and there's quite a lot of them. There are, well, 683 of them or something. Thinking carefully about double counting. 603 of them. How many possibilities are there? So that was part 1. How many squares? It's my first idea. Think about how many squares there are. And then, next idea, how many possibilities for the 2nd, 4th, 6th digits? And this is related to something we talked about a couple of weeks ago on the show. For the 2nd digit, I've no idea. There's sort of 10 possibilities for what that digit could be in base 10. For the 4th digit, there's, I guess, 10 possibilities. I've no idea what's going on with the 4th digit over there. But for the last digit,
not that many options.
Yeah, for the last digit of the square, we know that can only be 0, 1, 4, 9, 6, or 5. So only 6 possibilities. This is something we looked at a couple of weeks ago about what digit square numbers end in base 10. Okay, so 6 possibilities there. And that means that overall, 10 times 10 times 6 is 600 possibilities for what you get, for what you see. Let's say what you see when I reveal the second, 4th, and 6th digits. So let's think now. So we've got 600 possibilities for what you might see when I reveal the 2nd, 4th, and 6th digits, but 683 different square numbers. So if you think about that a bit, there's got to be 2 square numbers that have the same digits revealed by this. It's like trying to, yeah, it's like the pigeonhole principle, which somebody in chat is very excited to see.
Oh yeah.
Well, because it's exciting. The thing to imagine here is trying to cram all of these 683 square numbers into 600 different buckets or little boxes to keep them in. There's 600 possibilities for what their digits could be. Can you keep them all apart and give them all different, make sure they've all got different 2nd, 4th, and 6th digits? No, you can't, because there's only 600 possibilities for what the 2nd, 4th, and 6th digits are, and there's loads of square numbers with 6 digits. Well, slightly more, 683-ish. That's why I should have memorised the square root of 10. I knew it was about 312 or something. I just need this to be bigger than 600 for this proof to work. Okay, so this is a proof by pigeonhole principle that I quite like, because this method proves that there are 2 that exist, but it doesn't tell me what they are. So sometimes in maths it's possible to prove stuff like this where with my proof I don't know what the square numbers are. I needed the email from Joshua to tell me what square numbers actually worked for this, but somehow you can sort of prove that there is a pair out there. You could do a similar thing for 8-digit squares and so on. This extends nicely and saves us from having to write any Haskell code, which I think someone was suggesting in chat earlier. Okay, that's the answer to the square problem I set as homework a couple of weeks ago.
That was fun.
I've got a couple of minutes to talk about. I want to talk about the cube problem as well, which involves going back to my PowerPoint. Unfortunately, it's very annoying. We're going to give this a go. If this all crashes, then I'm really sorry. So the idea of the cube problem from episode 1 was. There's this way of drawing nice shapes, nice networks of edges onto the faces of a cube, so that when you put it all together, you get a kind of picture that's like a platonic solids. I'm not on the right side, am I? I'm still on this. Yeah.
Yeah.
Here's a picture. Stalling. So somebody wrote in. Sophie wrote in. Sophie accepted my challenge of trying to make all of the platonic solids, and made
Oh, this is
these,
beautiful.
which are great. So let me explain how the challenge worked, just for people who weren't here last week. The rules that Sophie's following to make these are your sides. Every face of the cube has got to have the same lines drawn on it. So here there's a plus drawn on each side, and that's going to have rotational symmetry by 180 degrees, like this one here, and the idea is you draw it on the faces of the cube, rotated by 90 degrees as you go across each face. And the challenge was to choose something to draw that would give you the kind of edge network, or a shape that's a bit like a platonic solid, or squashed down. So there are some lovely examples from Sophie, who's also coloured them in rather nicely. I really like this icosahedron one, especially. The idea of the icosahedron is you've got lots of triangles. So you've got like a green triangle here and a purple triangle here. Then the thing wrapping around the corner is also a triangle, which is hard to think about, but it is also a triangle. And there's 5 joining up at each point. So it's kind of like an icosahedron that's been squashed onto a cube in a nice symmetric way. We've really exploited the symmetries of an icosahedron. The extension challenge was to think about making some Archimedean solids as well. Sophie had to go at some of those as well. So here's some more nice shapes. I particularly like this small rhomby octahedron. So it's made of squares and triangles, but because we've squashed it onto the cube like this, even the triangles look a bit like squares.
Looks like cubes.
Yeah, right. This kind of is
Those
a triangle.
colours are so beautiful, though.
Yeah,
Like, they just
nicely
really make
chosen.
it so great.
So this is a triangle. Look, this one you can see a bit more clearly because it's got a corner here, and then this is an edge, and then a corner, and then an edge, and a corner, and an edge. That's kind of a triangle that's been smeared over a cube. So it's pretty good. I was going to show you. I'm running out of time. I was going to show you. There's this list of Archimedean solids for people to try at home. I think I'm not going to spoil this though. I showed a few of these. Ooh. Let's do a couple just to sort of show what you might do. So here's Sophie's solution for a tetrahedron. Looks like this.
Whoa, good.
Okay. So just putting a diagonal line on gave us a tetrahedron. That was this one. Nice. If we want a truncated tetrahedron, that's a tetrahedron with the corners cut off, then we just need to identify the corners and chop them off. So I think if we do something like this, we get a truncated tetrahedron. And you can build the rest of the Archimedean solids by thinking carefully about how they're related to the platonic solids. For example, when I see this rhomby, no, we talked about the rhomby cube octahedron. There it is with all its squares. But you can kind of see how to squash it onto a cube. Sophie's in chat as well. Hi, Sophie. There are ones that kind of remind me a bit of a dodecahedron, like this one, where I'd sort of start with the picture for a dodecahedron and try and work out how to adapt it. So this has got lots of triangles on. I might try and draw triangles that kind of join up like this. Maybe put a triangle around this side. So I can draw something like this for my triangle going around the outside. This is a terrible picture. Okay, and then I don't want this bit or that bit. So I can sort of build them out of the solids, build them out of the ones that we had before. Cool. This one looks like a football. Okay, that's all the time we've got.
That's literally football, isn't it?
Yeah, it's the classic football shape. That's the time that we've got. I'm going to turn this off before PowerPoint breaks my computer for good. Thank you very much to David for coming on the show and doing some math questions that David's never seen before.
Happy to be here.
Thanks for coming on. Maybe see you again at some other point. Now that we've got the technology for having guests on, I'm going to try and have more guests on. Also, it's term time, so we've got more students around. And I'm going to finish... Oh, look, come on, let's do this one. Is there Is there a term for this? No, I've no idea what this is called. If you can find out what this is called, please let me know. Our contact detail is oomc@maths.oxford.uk. That's an email address you can send us. If we haven't answered your question below, you can send it to that email address. Get in touch with us. Otherwise, we'll see you in 167 hours for the next episode of the Oxford Online Maths Club. Bye.
Bye.
And once again, I've forgotten how to turn it off. This is episode 2, and I still haven't worked out how to turn it off. We can do this.
That's fine.
I play the stinger, and it goes.
So it's still playing.
We're still live. Please don't swear or divide by 0.
Okay, no one.